Today we'll present our project on adiabatic inversion in pulsed arterial spin labeling. We'll present a short summary of our work before going into details. So in our project, we systematically varied hyperbolic second adiabatic pulse parameters such as B1 max, pulse order, beta, mu, and duration, and measured inversion efficiency in PASL. We saw that these parameters have to jointly satisfy the adiabatic condition, otherwise the inversion degrades. For designs that do satisfy the condition, inversion is fairly robust to B0 offsets, but still sensitive to B1 scaling. For PASL kinetic model, we showed that lower alpha directly reduces delta magnetization and SNR, leading to systematic CBF underestimation in low B1 regions. ASL is a fully non-invasive MRI method that measures cerebral perfusion by magnetically tagging inflow in arterial blood instead of injecting contrast. Subtracting label and control images gives us a quantitative CBF map like the example in Figure 1 on the right. Because blood flow changes track metabolic demand, ASL is useful for both studying normal brain function and for detecting disease, such as ischemic penumbra in Figure 2. The key technical challenge is achieving reliable longitudinal inversion of arterial blood despite B1, B0 inhomogeneity and a rough pulse design. Adiabatic inversion pulses are designed to handle RF imperfections, but their performance is very sensitive to how we choose the envelope and frequency sweep. That directly impacts labeling efficiency, SNR, and CBF accuracy, motivating our goals. First, we want to model the magnetization dynamics in PASL using the same core MRI principles within in class. Second, we simulate adiabatic inversion pulses using block equations and perform parametric sweeps over peak B1, pulse duration, and modulation shape. Third, for each pulse design, we evaluate trade-offs between inversion efficiency, robustness, and expected SNR. And finally, we connect this back to physiology by quantifying how adiabatic pulses can mitigate CBF errors caused by B1 inhomogeneity. So the end goal is more reliable perfusion measurements in realistic and perfect conditions. There are three main ASL schemes, and here we are focusing on pulsed ASL. It uses short spatially selective inversion pulse applied to a slab just below the imaging region. The RF is brief and low power, so PASL has low SAR, is safer at high field, and produces fewer MT effects, letting us keep the label imaging gap small and reduce T1 relaxation losses. The trade-off is a smaller labeled bolus, so PASL is less sensitive than other schemes and depends more critically on efficient inversion, exactly why we focus on pulse design. Figure 5 shows a typical PASL sequence. Tag pulse, wait through T1, TI, then interleave tag and control readouts within TR.
So for a little bit of background on adiabatic inversion specifically, in a rotating frame, the block equations in Figure 7 describe how magnetization precesses around the effective field BF with respect to changes in RF amplitude and frequency sweep over the pulse duration. If the rotation is slow enough to fulfill the adiabatic condition, magnetization stays aligned with the effective field and is carried from positive M0 to negative M0, producing a robust inversion even under B1 and B0 inhomogeneity. Figure 8 plots A through C show how the effective magnetic field rotate from positive Z to negative Z during an adiabatic inversion pulse. It also shows how the magnetization doesn't align with the effective field in the non-adiabatic case. For the most critical moment of inversion, when the frequency sweep crosses resonance, Bx equals 0. So the effective field is dominated by the B1 term. So that's why you see that in later slides, we only reference B1. For our method, our simulation method follows this block diagram. So we implement the adiabatic inversion pulse as a hyperbolic secant with the following equations to represent the amplitude envelope and frequency sweep on the left. In our experiments, we vary the following pulse design parameters. So pulse order, maximum B1 amplitude, pulse width, and frequency sweep amplitude, as well as pulse duration. And then we implement the block simulations and provide analysis on how the design parameters impact inversion, as well as generating a PASL kinetic model. For our experimental results, first we analyze the inversion efficiency under B1 and B0 variations. So here we use HS10, so pulse order of 10, and we defined inversion efficiency as alpha equals 1 minus the final longitudinal magnetization divided by 2. So if MZ final is 1, then alpha equals 0, and their inversion efficiency is poor. And then if MZ final is -1, then alpha equals 0, and we get completely efficient inversion. For the heat map in figure 11, we can see that larger B1 scaling produces near perfect inversion with high efficiency because it fulfills the adiabatic condition better. And then for smaller B1 scaling, the opposite is true because the adiabatic condition isn't met. Lastly, we see that the color remains constant in the B0 direction, meaning that inversion is largely insensitive to moderate B0 offsets. And this also tells us that HS10 specifically is robust to off resonance within the sweep bandwidth. Next, we're going to talk a little bit about what happens when we vary B1 max over pulse orders 1, 4, and 10. So the frequency sweep and HS envelopes used in these experiments are illustrated in figure 9. And then from figure 10, we see that the HS10 achieves smoother, more stable inversion because a higher pulse order produces a more narrow and steep envelope that more easily satisfies the adiabatic condition. This makes it significantly more robust to B1 variations, and then even under poor RF conditions like in HS4, the inversion is still relatively robust and can at least achieve partial inversion. Also, when we increase the B1 amplitude magnification, our inversion improves immensely. So in the HS10 plot, we can see that when we multiply the magnitude by 1.5, it completely inverts from 1 to -1 rather than like slightly less. And then next, we see what happens when we vary beta or mu. So here we choose a sufficiently large B1 max when sweeping beta or mu so that we can isolate their effects and analyze what happens. For this specific set of fixed parameters, we found that beta equals 2 had the best inversion. And then when beta was too large, the envelope was too narrow, meaning that the pulse moves too fast and the spin can't follow the effective field. And that doesn't fulfill the adiabatic condition either, so we only get partial inversion. When beta is too small, the RF envelope is too broad during the resonance crossing moment, so that also doesn't satisfy the adiabatic condition, and we see oscillatory behavior. And then next, when we varied mu instead, mu equals 100 had the best inversion, and this is because it also produced a more narrow and gentle sweep. However, this is only true for on-resonance spins where B0 equals 0. If there are off-resonance spins, when mu is too small, they don't experience the RF frequency crossing their resonance, which leads to poor inversion. And then when mu is large, the wide sweep created faster change in angle per unit time, which hurts adiabaticity and hurts inversion.
Okay, so we did another block simulation with focus on the block trajectory, the PASL labeling efficiency, and the PASL general kinetic model. So the general kinetic model here is the perfusion weighted signal delta n, which represents the arterial transit time and a lot of other design parameters that shows the cerebral blood flow. So here we use a HS1 adiabatic inversion pulse with duration at 15 milliseconds, peak B1 13.5 microtesla, beta equals 10, and mu equals 5, providing an inversion bandwidth approximately 4K hertz. We first changed the cerebral blood flow, so it ranging from 60 to 20 into 80 microliter per 100 grams of tissue per minute. As we can see, the delta n changes accordingly to how much blood flow in the cerebral. And for the gray matter, it's roughly the 80 microliters one, and for white matter is 20 milliliters one. And with higher cerebral blood flow, the delta n will increase accordingly. We changed the inversion pulse duration. So the reference inversion pulse duration is at 15 milliseconds, which creates a block trajectory like the bottom left. And this is slightly above the standard. And as we see, there's a broken trajectories, which is induced by the pulse duration not filling the adiabatic inversion condition. So the inversion magnetization doesn't follow the inversion pulse. And we also simulate 10, which is within the standard where we see no broken trajectories and the magnetization was perfect. And for shorter duration, 1 milliseconds, the inversion pulse was just too fast and the inversion doesn't satisfy 180 degree for longer duration. That just one pulse become too sharp So the adiabatic condition wasn't satisfied, and there's so many broken trajectories, indicating that the B1 homogeneity does matter for this condition, and it becomes a non-adiabatic case. This is a more intuitive illustration of how pulse duration affects the labeling efficiency. So the bottom left is what happens in the 15 milliseconds, and the right two figures was around 20 milliseconds to 23 milliseconds. Even though there's a decrease in labeling efficiency, it still maintains above around 60%, while the ones in the middle is for 1 milliseconds, which is way off, as the labeling efficiency was around 20% because inversion wasn't completed with such short duration. We then add noise and SNR. So for Gaussian noise, the SNR is less than 2 throughout the graph, which is correspond consistent to what we have for PASL. The SNR is relatively low. It rises sharply after 0.7 seconds and peaks around 1.6 to 1.8 seconds, then slowly decays as it enters the imaging slab. The single shot PASL without background suppression has inherently low SNR, which is the fundamental reason on why multi-TI schemes or background suppressions are used clinically. Key takeaways and future work. To ensure efficient inversion, adiabatic pulse design parameters must be chosen carefully to balance and fulfill the adiabatic inversion. So for example, if B1 max is too low, beta mu and pulse duration must be adjusted to compensate. Otherwise, the spins will not follow effective field. The labeling efficiency is controlled by the inversion pulse performance with a combination of duration, B1 max, beta, and mu. So for future, we could use other labeling themes to simulate, but for now, PASL is currently the most practical labeling theme, even though it was lowest SNR among 3. It has high labeling efficiency, which make it the recommended standard in clinical use. We can also use different pulse designs to compare to HS1 or use higher order HS or TRFOCI. And for reference, we did use AI for our code, and that is all.